Hi, today we're going to talk about polarity and covalent bonds and how that relates to an intermolecular force. So before we begin, I need you to get out your reference table, and you must have your reference table for this. I didn't get mine. Give me a moment. When you're looking at your reference table, you need to make sure that you're opening it up to table S, because you're going to need to look at electronegativity values. So what I'm going to do is I'm going to use water as an example throughout this entire process. And if I draw a water correctly, this is the way that it looks like in nature. In fact, it has a 105-degree angle, and we'll get into the details of that in a lab in the future. So what we're going to do when we try to figure out polarity is you're going to look at the electronegativity values for each one of the atoms in this molecule. So I'm going to use table S, and I'm going to look at the electronegativity values, which are in this column right here. And I'm going to look at hydrogen. Hydrogen has 2.2. So both of the hydrogens have a 2.2 for electronegativity. Then I'm going to look at oxygen. And oxygen is going to have a 3.4. And if there is a relatively large difference, any difference between numbers, if it's greater than 0.3 or 0.4, it's going to be a difference in electronegativity. And what that means, remember, electronegativity means that it wants electrons in a bond. So this oxygen is actually hogging a lot of the electrons. So what's happening is it's creating a negative cloud because more of the electrons are going to be hanging out by the oxygen than they are by the hydrogens. So there's an uneven sharing of electrons. So the oxygen is going to be slightly negative, and the hydrogen is going to be slightly positive. Because, again, this difference in electronegativity. The electrons are going that way, towards the oxygen. This is supposed to represent a little positive. Now I'm going to show you another example. This is something that is polar. It is polar because it has different ends. Like we have the North and the South Pole. We have poles on a magnet. We have a positive and a negative pole. That's where we get the name polar from. We have an area that is positively charged. We have an area that is negatively charged. So these have polar bonds because they're different, and there's a difference in electronegativity. And we have a polar molecule because we have an area that is negative and areas that are slightly positive. I'm going to show you an example of something that is not polar. So we have carbon dioxide, which if you draw it correctly is going to look like this. Now I'm going to use my electronegativity values from table S, and I'm going to write them down next to my elements. So I have carbon, which is again 2.6. And I have oxygen, which is 3.4, and again 3.4. So what's happening here? First of all, the oxygen is taking the electrons. So I have a negative end over here, and a negative end over here, and a positive end in the middle. Because our carbon dioxide is symmetrical, and symmetrical basically means that you can divide it in half and it looks the same. So because this is symmetrical, these negative charges are canceled out. This negative is canceled out by the other one, it's canceled out by the positive in the middle. This specific compound contains polar bonds, but because it is symmetrical, it is a non-polar molecule. An example of a non-polar bond, we're going to use bromine. And when you look at bromine, you're going to notice that the electronegativity value is 3.0 for both of them. Because they have the same value, there's no difference in electronegativity. So neither one of these atoms is going to be pulling the electrons in any one direction. So this is considered a non-polar bond, and because it has non-polar bonds, it's a non-polar molecule. In fact, the only elements that have non-polar bonds are the Hofbrinkels: hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. In addition, A bond between a carbon and a hydrogen is also considered nonpolar because carbon is 2.6 and hydrogen is 2.2, which is a very small difference. It is a difference of 0.4. So technically, in the scientific community, this is considered also a nonpolar bond. However, on the Regents, this is going to be your answer. Now, let's go back to our example of water. Because water is polar, you're going to have an area that is positive and an area that is negative. Again, the oxygens are negative and the hydrogens are positive. So because of this phenomenon, what's going to happen is water is going to stick to itself. The negative ends of the oxygen are going to stick to the positive ends of the hydrogen. And you're going to have a big giant network of connected compounds. And because of this is why water has many of the characteristics that it does have. Many of the physical properties are because of its polarity. But we also consider this type of attraction is called a hydrogen bond. A hydrogen bond is a strong intermolecular force. Anything that is polar, like water. Also, ammonia is also polar. If you draw these out, they do not have a symmetrical shape. Because they don't have a symmetrical shape, they will exhibit hydrogen bonding. They also have higher boiling points than something that is nonpolar. One last thing. If we're looking at boiling points, for example, fluorine at room temperature is a gas. Bromine at room temperature is a liquid, and iodine at room temperature is a solid. Because fluorine is a gas, the particles are not sticking to each other. They're all over the place because it has lower intermolecular forces. Bromine is in the liquid phase. It has a medium intermolecular force. And finally, iodine is in a solid phase. It has the highest molecular forces of any of the group 17 elements. There are some practice problems. Look over there.